Alkenes can also be hydrated, which means that they can add a water molecule. In other words, the fragments of water molecule, an OH group and hydrogen atom, over the double bonds. The mechanism of this reaction is rather similar to the mechanism of hydration of addition of HX moieties. The first step is protonation from water, where we get cation. And it's here. And the second step is addition of this water molecule onto the cation to give us protonated alcohol, which is then deprotonated through reaction with another water molecule, which takes off the proton to give us finally the product alcohol. And if you think about this mechanism, you will notice that this looks remarkably similar to the mechanism of alcohol dehydration, where the first step is protonation, so exact reverse of this. Then we get the protonated alcohol, which then loses water to give us a carbocation, which is then deprotonated again to give us an alkene. So these two reactions have exactly the same mechanism, just operating in reverse. And this is an illustration of the so-called principle of microscopic reversibility. Which states that if a given reaction or a process in general goes through a certain sequence of steps on its way forward, the reverse process will go through the same sequence of steps, just in the opposite order, on its way backward. And the energies of the corresponding intermediates will be exactly the same. Now, if we think about the mechanism of this, we will quickly realize that hydration of alkenes is also subject to Markovnikov's rule. Because if we look at an asymmetric alkene such as this one, it can get protonated in two positions. It can get protonated on the more substituted carbon to give us a less stable cation. This will be a secondary cation. Or it can get protonated at less substituted carbon, leaving the cationic center on the more substituted tertiary position. Of course, this one is more stable. And so this is the one which goes on to give us product after water addition and deprotonation. And so we do get Markovnikov product in majority of cases. Again, because we're forming a more stable intermediate. Now, we'll get back to this mechanism in a minute, but before we get there, we should really consider one thing that should by now be pretty apparent, and that is that if we treat an alcohol with an acid catalyst, we'll be able to deprotonate it and get alkene and water. And the same will happen, well, the reverse reaction will happen if we treat an alkene and water with exactly the same conditions. And so how do we get any of these reactions to work, because they're both in equilibrium? Well, in order to analyze, to understand that, we need to realize that as we go towards alkene and water, our entropy increases, because we go from one particle to two particles, which now have a large number of degrees of freedom. Which means in all reactions that proceed with an increase in entropy, prefer higher temperatures, because higher temperatures increase the contribution of the entropical component to delta G. Also, if we start removing water, which is possible, then that will drive this reaction towards an alkene. We could drive the reaction in the opposite direction by lower temperatures and by the addition of excess water, which will then lead to alcohol hydration. Now, this reaction proceeds through cations. So, and then cations, as we already know, lead to rearrangements, which means that oftentimes we don't get really necessarily the product that we want. And in our next subtopic, we will encounter a reaction known as oxymercuration demercuration, which allows us to get the same Markovnikov type products from alkene hydration, but without the cations. And then this modification avoids the cations and thus avoids all the problems that are associated with cations, typically those of rearrangement.